Okay, we are going to start learning target number 3. There's probably going to be a couple of videos with this learning target, only about up to 15 minutes long. And this one is dealing with patterns and nonlinear functions. We've talked about linear functions, so now we need to move on to nonlinear functions. So we're going to first look at the definition of a nonlinear function. And think about what nonlinear sounds like. It's not linear. So the definition for a nonlinear function is a function whose graph is not a line or part of a line. So nonlinear function will not be a line or even part of a line. Now I have a concept summary box here that is really good to look at. It compares linear functions to nonlinear functions. You've got both the definitions there for you. Now, linear functions, one thing that we discussed was that linear functions had to be non-vertical. Okay, that's a vocabulary term we talked about, not vertical. It cannot run north and south. So notice that this one is a horizontal line, so that is considered a linear function. But all of these, even if we don't connect the dots, form a line. Now, our nonlinear function, the definition we just wrote, was that it's not a line, and you can clearly see that each one of these illustrations is not a line. Now, even though this one appears to be part of a line, when you put it together as its entire function, this is nonlinear because it does turn right back around and increase. So, these are some examples of nonlinear functions. Now, the linear, one thing that we can think about, and we discussed it in the last video, is if you notice these dots here decrease at what appears to be a constant rate, and it's constantly decreasing over time forever and ever here. And so that is a good example of linear. With nonlinear, if you notice like this one, it's decreasing, but it could decrease rather quickly and then slow down, and then all of a sudden it starts increasing a little bit and then increasing very quickly. So it's nonlinear, it's not creating a line, and it's also not constant. This one appears to be constant, so we would think, oh, this is a line, but then all of a sudden it turns right back around and starts increasing. Even though it's still at a constant rate, it does change directions. So these are some examples, some things to think about when dealing with linear and nonlinear. So let's look at our first problem. In this problem, we want to classify functions as linear and nonlinear. So we're actually going to analyze our tables, and we're going to graph them. Now, in the first table, we're talking about the area of a pizza is a function of its radius. Okay, so let's think about what that means actually. This will help us with our graph. Which one of these is going to be the dependent variable? Which one depends on the other one? Well, the radius, if you're making a pizza, you can make the radius whatever you want it to be, but the area of that pizza is going to depend on what the radius is of the pizza you chose to make. So our area is actually going to be our y value, and our radius is our x value because it is our independent function, or independent variable, excuse me, in our function. So this one, same thing as this one. Let's look at this one. The weight of the cost of the pizza sauce is a function of the weight. So which one of these is going to be your dependent variable? Which one depends on the other? And the cost of your sauce is your y value. Looks like an X. The cost of your sauce is your y value because that is your your dependent variable. It depends on the weight of the sauce. So that means your sauce is your independent variable. Sorry, I'm going to get you confused there. Your x value is your independent variable, and that is the weight of your sauce. Your x value, or your y value here, is your y value here, try to clear this up, is your dependent variable because it depends on the weight of your sauce. Your cost is going to depend on the weight. Alright, so let's actually graph these. Let's start with this first one. So our x is going to be our radius. So I'm going to put radius down here. And our area is our y-axis. I'm going to put area there. Alright, so let's go ahead and fill these in. 2, 4, 6, 8, 10. Well, the x-axis is very easy to fill in. This is going to be 2, 4, 6, 8, 10. So I'm just going to mark 2, 4, 6, 8, and 10. I'm just labeling every other one there. And then our y values, let's figure out what's going on here. We're going 12.57, then 50.27, then 113.10. So it doesn't appear to be increasing at the same amount. So it also looks like it takes a rather big jump between 50.27 and 113.10, and then another fairly large jump. So we're increasing very quickly here. So we've also got to go from 12.57 all the way to 314.16 very quickly on our y-axis. So it is going to be a little more difficult to set up our y-axis. So let's do this. Let's mark off our y-axis in increments of 50. Now that's going to make the first one a little more difficult, but we'll be able to do that. I don't think that'll be a big deal for us. So this is going to be, here's 50, so this will be 100, so 150, 200, 250, 300, and even though we go above 300, I think we'll be okay there. So let's mark this. Let's see. This should be 100 right here. 150. That's 200, 250, 300. I shouldn't have written area so close to my problem there, but so make sure you know this one is 200 here. Alright, so let's graph this. Let's see. We've got 2, 12.57. So here's my 2. Here's my 50. So 12.57 is going to be somewhere down here. So we're going to have to make it not going to be the easiest, so somewhere down here. Alright, now let's see. We've got 4. For 4 is going to be 50.27. So here's our 50. So 4 is going to be right about there. 6 is 113.10. So here's our 100 and here's our 150. So we're probably somewhere around there. For 8, we have 201. So there's 50, 100, 150, 200. So for 8, we're almost on that 200 mark. And then for 10, we're at 314. So here's our 300. So we're going to go over our 300 mark a little bit. And if you notice, some people try to force these dots all on the same line, especially since we're not perfect. We can't necessarily make it exactly right. But if you notice, they're not increasing at a constant rate, and they really aren't forming a line. So if we go to connect this the best we can, it does actually curve, and I missed my dots there, but it does actually curve up. So this is an example of non-linear. Lost my eye there. Non-linear. Now let's go to our sauce. The weight is 2, 4, 6, 8, and 10, and our cost 80, 160, 240, 320, and $4. So our cost, let's look at this again. 80 to 160, that's 80 cents. 160 to 240, that's another 80 cents. 240 to 320, that's also another 80 cents. And then from $3.20 to 40, that's another 80 cents. So I'm actually increasing by the same amount every single time. Our cost is increasing at a constant rate. So that should kind of give us a thought that this is going to more than likely be linear. But we have to graph it and determine that first. Okay, so the weight is our x, and cost is our y. Alright, weight 2, 4, 6, 8, 10, exactly the same thing as it was with the other one. So that's pretty easy. We should be able to just do 2, 4, 6, 8, 10. Again, I'm only filling in every other one there. But now our cost, we're going from 80 cents to $4. So it's really not too big of a jump. So I think we should go ahead and just mark this off in increments of 1. So this would be $1, $2, $3, and $4. And $4 is actually our cap, so I'm going to stop there. So that's my $4. This is $2. So the first one is 1. So let's actually plot these points. At 2 ounces, it's going to cost us 80 cents. Now this is a dollar right here. So at 2 ounces, 80 cents, probably somewhere around in there. For 4 ounces, it's going to cost us $1.60. Here's $2, so $2.50 would be in the middle. So we're a little above the middle, but there's for 4 ounces. For 6 ounces, it's $2.40. So there's my $2 mark, my $3 mark. So somewhere close to halfway. For 8 ounces, it's $3.20, so $3.20 above the $3 mark, not really quite halfway, but somewhere right in there. And then for $10 is exactly, or for 10 ounces is exactly $4. So 10 ounces, $4, something about right there. Now, even though we're not perfect and our dots are not exact, if you notice they are increasing at about the same amount, about 80 cents. Well, it is 80 cents based on our table, so it is staying constant. And if we were to connect these dots, it does form a line. So this is an example of a linear function. So take what you've seen here with nonlinear and linear. Hopefully your graphs look a lot better than mine. And I want you to apply that to your turn problem 1. You've got your table here where you're cutting paper and you've got a fraction of the original area remaining. So if you cut it once, you've cut it in half. That's that first part. So notice that all of these are in fraction forms. So your y value is in fraction form. So you should really be able to set up your graph, and 1 should be probably the very top of your y-axis, and all the increments below that should be your fractions. You could make this a lot easier on yourself that way. So graph this function and then label it as either linear or nonlinear. And once you finish this problem, please go on to the second video for this learning target for the last couple of problems and your summary question.